Hey everybody, this is Larry. This is day 18 of the Leetcode July Daily Challenge. Hit the like button, hit the subscribe button, join me in Discord, let me know what you think about today's problem. Today we have a hard problem, so it's gonna be a little bit long, a little bit tricky. Let me get a water real quick. I ran about 4 miles today just to give an update, but it's still very hot here in my apartment, and also, yeah, my eyes are so tired. I need to take. I should have taken a nap beforehand. I guess that's the other story. But yeah, let's take a look at today's farm. I don't really have much to say. Just 4 easy miles, very slow miles on the treadmill. It is nasty today, and yeah, and that's it. Let's take a look at today's farm. We have 2163 minimum difference in sum after removal of elements. Yeah, and I'll remind you to hit the like button because I like to be liked. No, I mean it's fine. Or if you don't like it, send it to someone you hate so that you waste their time. That's my story. Okay. Anyway, okay. So you're given an index, integer index array nums 3 times n elements, 3n elements. Remove any subsequence. A lot of subsequence problem lately. Maybe that's the idea. I don't know what it means. Any subsequence of element of size exactly n from nums. The remaining 2 times n will be divided into 2 equal parts. First n belong to the first part, the second n elements belong to the second part, and then the difference between those sums is this thing. But it could be negative. It's really awkward because I don't. I think difference is like I mean, I don't know, in English and stuff like that, it's a little bit tricky in terms of that, like, because if you try to find minimum differences, that means that, I mean some different things, right? Meaning that you want, because minimum difference, I get that difference means a minus b, etc., like subtraction and stuff, but minimum difference also, like, linguistically, for me anyway, maybe I'm wrong on this, and that's fine. I just feel like if you mean, like, it's the smallest delta, like the smallest difference between 2 sets of numbers, and not, in this case, technically speaking, you have some first, some left. I think left is more straightforward if you ask me also. Some left minus some right, then technically you have this, let me write it out actually. Let's just say you have left sum minus right sum is what we're trying to optimize and minimize, right? And of course, in this way, the immediate dot is that if, and I don't know if this applies here, but that is my first dot. And I, for these videos, especially for hard problems, I don't always know the solution like immediately. So I have to think through this a little bit, but I am going through my dot process. This is live. This is the point of this channel, because I think, and you could also, in another way, I think you could also think of it as me, like, if you were interviewing me, this is how I would describe it. Sometimes like, you don't need to go on an interview. You don't need to go for all the details all the time unless they ask you for it. So sometimes it is missed. But, I just want to show you my thought process, right? Because for me, it is more interesting than, like, you could click on, if you just want the solution, if you just want an quote-unquote explanation, you could click on editorials, you could click on solution, you could click on a lot of things, maybe other YouTubes. Feel free, if you feel like that's more helpful for you, watch those videos. If you want to just watch someone solving it live and usually getting the problems, then this is how I think about it. Anyway, I just want to add that caveat because inevitably sometimes whenever I don't know the solution already, or not that I know them anyway, but like immediately, there are a lot of problems where I just immediately get it. But for this one, not yet. Anyway, my point, the reason why I have so much caveat is because, like I said, every time I don't have a problem, that I immediately get people always like, oh, why don't you make a video like another person? I'm like, well, why don't you just watch their video then? Why are you watching this video? My point is that my channel is meant to be different. In any case, okay. That said, so here we have to minimize this function, right? And there's really 2 ways to minimize this, or 2 things that you can do together, right? Which is minimize left sum and also maximize right sum, right? I think that's straightforward, right? Because this gives you the smallest number here and the largest number here, so that this has to quote unquote the biggest negative, which is the minimum number. Yeah, which linguistically is a little bit awkward. But in any case, okay. Okay, so that's the first thing that, I mean, I don't know if it's an observation with this problem yet, but that's a guideline for what I want to do. Yeah, and then now we have, maybe we look at some examples because I don't know. Okay, so and for this, I think even if you know the solution, you should play around with examples a little bit just so that you understand it. Given that I did take a peek, just to be clear, at n, and n is 10 to the 5th, right? Which means that, well, what does that mean? That means that n squared itself is too slow. So you have to do something either of n or n log n, or maybe n times square root of n or log square n. But like, something sub n squared for sure. Maybe, the degree of how fast you need to be, maybe it depends. So in that case, there is usually some element of greedy-ish things, so you have to play around to figure it out. I mean, it may not be greedy in the sense that, like, you're like, oh, it's greedy, and then you get it, right? There's a lot of ways to do greedy, and for me anyway, I'm really bad at greedy problems. I'm always trying to, especially on the video, I can't just be like, oh, let me YOLO. I mean, I do say that a lot, but I try to at least have some basis of why I'm YOLOing, right? But in any case, so yeah, let's play around with this. This should be straightforward, right? Because we want to, like we said, we want to minimize left sum, we want to maximize right sum. So we remove 3, then now, wait, did I misunderstood this? Let me double check. Sum of the two parts is min. Okay, so this is from just removing this. Okay, which is -1. Yeah, that's what I was going to say, but without. I mean, they did it by choosing every possibility, but we don't have to, I suppose. But yeah, okay. But yeah, we just removed the 3, then now you minimize the left, and then you maximize the right, and you're Gucci, right? Okay, so I don't think, so understanding is fine. So then here we do another one, right? I already have a quick intuition. I don't know if this is going to work, but something about like, because there's 3 times n, maybe we go simultaneously from the left and to the right in terms of choosing something to remove. Actually, let me double check. You could remove from anywhere. I don't know. Yeah, I don't know. Still don't know. Okay, so, and now maybe for example 2, I don't want to look at the answer yet and maybe just play around with some strategy. I have some idea, like I said, about going from left to right at the same time, but I don't think it's anything concrete or solid enough for me to go, right? Here again, we don't minimize left sum. What is... I think for problems like this also, it's important to have some sort of invariant, right? What is an invariant of this problem? What is an invariant of these processes, right? And what I mean by that is that, okay, what is an invariant? An invariant is something that doesn't change in the entire problem, even if you iterate, as you make modifications, etc., right? In this case, for me, it'll be like a for loop. And one observation that I noticed, and I don't know if this is useful, sometimes you make like 20 observations, and if 3 of them are useful, it's still good, right? Like if 3 of them are useful, then and they are the 3 that you need to solve the problems, then that is good. Yeah, and for me to make a main observation is that, okay, let's say we have this n element, we can divide them to thirds, right? What does that mean? Well, if we divide them by thirds, then now the first 2 numbers by pigeonhole principle has to be in the left sum, right? And also in the same notion, the numbers on the right by pigeonhole has to be on the right sum. And the proof is, I mean, you could probably write a more rigorous proof, but the idea is that, okay, you can only remove 2 elements, right? Sorry, let me rephrase this. Maybe I didn't write this clear enough. It's not that these 2 items has to be on the right, but if we include these 2 items, they have to be on the right. Meaning that these 2 items, no matter what, they cannot be on the left side, right? And the proof I said is going to be straightforward. Let's say you remove any 2 numbers to the left, no matter what. Well, these numbers will be on the right, right? And that's it. That's basically the idea of our proof. It doesn't matter which numbers you remove, the one three will be on the right, and same thing on the left side with our loss of generality. You remove any two numbers, it's still 7. 7 will only ever be on the left, and 9 will only ever be on the left. Is this useful? I want to say so, because then now you can almost start off by saying, okay, the first third, and I don't know if this is true. Work with me here. I'm doing this live. This is me, a little bit of a brainstorm, to be frank. So if I go the wrong path, my apologies. But like I said, I'm not trying to. This video is not necessary for you to understand the solution. It is more about like going through the thought process of what I'm going through, right? And I'm going a little bit, like, yeah. That's basically my idea. Anyway, so if this left, then maybe we can. The idea now then is that, okay, if these things can only be on the left and this can only be on the right, what if we started off that way, right? And then the idea then is that, can I do or create some sort of a swap function, right? And like I said, I don't know that it is possible, or I don't know that this is easy or possible, but I'm just thinking through the dot logic, or whether it, or you have to prove correctness or something like that. But I'm just playing through some ideas. And here, for example, you want to minimize the left sum, and 7 and 9 can only be on the left. So maybe you would say, okay, well, there's a 5. Can we replace this? And the answer is yes. You can replace the 9 with the 5, right? So then now replace with a 5, and then now you have an 8. Can you replace? No, but you can, maximize the right sum by here. The only reason why I'm not super confident about this is that, technically speaking, there is more mathematics. Like there's, like the way that I did the decision is order dependent, which I don't like, right? Meaning that, or maybe it's not order dependent, but at least like it is not clear to me that it is not order dependent, right? Or order dependent or order independent. I don't know. My point is that order may matter in terms of like how you get it, right? For example, you can maybe say, oh, well, we choose the 8 then first, and going to the right, and actually for this one, I'm not convinced that was the best anyway, and I just didn't look at the answer. Like for example, you can imagine going 5, 8 here, for example, right? And maybe that's a better fit. And there is some like minor, like in terms of decisions, that this is why this is trick, is that there is a decision. We talk about decisions a lot on this channel. That's how I think about things, because the choices are not forced, at least not immediately clear to me, right? Because for example, yeah, I mean, you could do some math. For example, 5. I think the part that is tricky is because, no, maybe that's fine. Maybe for every number, and well, the thing about this is that um 5 can be on the right side, right? That's what I mean by, like, if you do this first, maybe it doesn't make sense. But then now you have to figure out how to process, or like what order do you process in the middle? Doesn't matter. And that part I'm not sure about, right? Because, for example, if you just do 5, well, you can't even compare it to the right, right? But maybe you don't have to. Maybe you just compare 5 to the left versus 8 to the right, right? Maybe you don't have to compare 5 and some implicit thing. And the reason I mean is that and this would obviously be greedy, and I don't know for sure. But what I mean is that, okay, well, if we move 8 to the right side, what is the gain? Well, you would obviously remove the 1, so that's a gain of 7. So putting 8 inside one of the 2 buckets, and you only have one choice, is not one of the 2 as a choice. You're putting it on the right side, whereas 5 on the left side, where you gain 4, right? Because putting 5 on the left side, you gain 4, because you replace the 9 with a 5. So that's kind of maybe an idea, but honestly, it still feels a little bit sketchy for me. Like, it's not, I don't feel certain. Another thing, of course, is that, or what happens if there's a tiebreaker, right? Because 5 goes to 9, and then maybe, let's say there's 7. Which one do you do first? right? I mean, maybe you can make a reason, and you have to maybe prove a little bit that like the order doesn't matter in this case. Like you could maybe just do both or whatever, because I don't know. But then what happens if there's like another number in the future that is smaller, right? I guess in that case, I mean, I'm not. I think maybe that is just case analysis, right? So, for example, let's just say we have an x in the middle, and let's just say that we have more numbers, but only these are the relevant numbers, because then now 7. Oh, I think I messed this up anyway. This is actually 1, and I mean, okay, let's just make this a 3, because I don't want to make this another 5, because that's just even more confusing. So let's say we have 3, 3. So then the impact 7 going to the right is 4, 5 going to the left is also 4, 5 matching with 9, right? And then now you have an x. And then I guess the scenario in this case is that, and this is very brute force in the sense of like going for everything. So there are only a couple of states. So then now we go 7, 3, 3, right? And that's one way of doing it. The other way of doing it again, then is just doing the 7. So you do this. So then 3, 7, right? And then another way of doing, and then now what do you do? Or we have to break it down case by case. That's how I do these proofs, because I'm not good enough to do it in like a pure mathematical way. So then now this thing is 4, right? So what if this is, so what I'm trying to do is try to construct a counterexample. What would be a value of x in which maybe x gets matched to the left, but the correct global, like locally you match x to the left, but globally you actually want x to the right, maybe, right? That means that this has to be, we want to minimize. So that means that let's say this is a smaller number, so maybe this is a 1. Well, in this case, 1 you would never, go that way. But in this case, maybe that's just like a quirk of the thing. And you could like just play around these cases, right? For example, let's just say it doesn't change anything. We add 100 to every number to the left side, right? Then now I'm going, okay, well, where we replace it, and then now, even though if x is, I don't know, 101 or something like that, then now replacing, or let's say 101, right? Because then now you minimize, the cost is 6, so then you would replace it with 101, 105, right? And then now you have a 7. Oh, I did the math wrong, sorry. Oh, no, that is right. But then now you have 3, 3, and then you replace the 7 on the right side, say, right? And then now you're done. Let me actually copy it over instead. Well, move it to the next step. And then now you're done, right? But the problem is that with this kind of construction is that you probably actually want the 101 to the right, right? Even though like here, you can see that this gives us an improvement of 6, which is better than an improvement of 4. But you can see that in a global way, what you actually want is 107, 105, and then 7, 101. And in this case, you can, like do some, you can just do the math really, right? It's this number minus this number, which is going to be positive. And this is also positive actually, but way less so because you have 101 subtracting on the side. So that means that we cannot do this kind of, I mean, this is just how I construct a counter example of, well, the idea of me doing some sort of greedy based on the edges is just wrong, right? Because we just showed you why one example is why is wrong. But I think there is still something to be said about this idea, of course. I maintain that. And maybe actually we can even put it in the test case before I change them, so that I can test case in the future. So 107, 109. I don't think I had, this wasn't the, oh yeah, no, that was right. Let's say 105, 101, and 733. This is incomplete, so I need to add more numbers. Just add another 3 and another 109. I think that's fine. Maybe not, but if this gives you drastically different things, we can change it in the future anyway. But yeah, but in this case, it's very clear that given these 3 numbers, you actually want to move all these 3 numbers to the right. But if you do some kind of greedy thing, maybe you actually move the 105 to the left instead, which is what we do not want, right? Okay, so let's go back. But I still think the idea here is kind of similar to what we want in terms of like this left-right invariant. And then it's just about figuring how to swap. And honestly, right now I am a little bit stuck. Maybe not. Let me take a look. Because then you have to figure out a split, right? Because that means that, oh, I'm just being dumb. Wait, am I being dumb? Because then now, I guess you can just do sliding window, right? Maybe that is it. That is it. Yeah, that is it. But this is through the same idea. I mean, I know that I spent a long time kind of showing you an incorrect, greedy solution, right? Obviously, in contest time, I might, be much faster about it because I'm explaining it in detail, etc. But I think another way is just sliding window, right? And the way that I was able to come up with this, and I think this is right, so now I think I know, it's just this is visualization. And visualization is just writing it out like this. As we said, we made the observation of the invariant that 7, 9 has to be on the left, and then 3, 3 has to be on the right. But then then maybe we can just draw a partition, right? And what does this partition mean? That means that now, here on the right side, we keep 7, 9 to the left and then keep this to the right. And what that means is that we have to remove n elements, right? So remove n elements. So you have this. That means that you have to remove n from the right, right? And then now the next step would be moving this divider to I guess here, right? And then now here you remove n-1 from the left and right. I mean, in this case, n-1 is 2, so maybe it's a little bit confusing, right? But then now the next step, it's going to be sliding window, right? We slide this, and then now we go, this. And then we want to remove n-2 numbers from the left, right? And that's it. And the reason why this is it is that, one, is that what are we doing, right? And with practice, this is how, if you think I'm going fast, it's because and I don't mean that in a humble brag way, it's just practice. But what I mean is that as soon as I saw this sliding window, I was like, oh, well, what does removing n from the right mean? That means that in this case, well, we already talked about, we want to maximize it. What does maximizing means? We remove the n smallest numbers from the right, right? And then similar, not actually, I guess you could either similar or exactly opposite, depending on how you want to define it, is that from the left side now, we want to minimize this, right? We want to minimize the sum of this, removing n-1 number. So what does that mean? We want to remove the biggest numbers, right, from the left side. n-1 biggest number in this or whatever, right? And of course, now the question is, you could say removal, but you could also say keep n, right? So maybe that's different. Maybe that's actually a little bit cleaner. Like I said, I'm showing this live, so sometime you go right. So keep n from left, keep n from the right, right? So maybe that is clearer because that is literally what they tell you to do anyway. But here now keep left. Remember, we're minimizing, so we want to just keep n smallest number, and then keep n from the right, which is we're maximizing. So we want to keep n maximal number. And that's it. That is the entire problem, because then now you're able to use this with a heap or something like that, right? With this particular problem, I'm not going to use a heap, at least in Python, because you can do it, but you just have to do it in a lazy way. And I don't mean lazy as in like you're lazy, but like lazy in a lazy propagation kind of way, if you want to call it that, for a heap, which is kind of a little bit, it's already complex enough. But in other languages, there are, or even in Python, if you want to write it that way, you could use like a binary search tree type thing of just getting the n smallest number and then just keep track of whether, you just keep track of stuff. But yeah, now that's basically the idea that we have, and now it's just implementation. About 24 minutes in. Okay. But for me, for now, I mean, I'm going to use this thing called sorted list, which is what it sounds like, a sorted list. And then from the left, but here we have to keep track of the sum and then the state of the add and remove rows, but that's fine, right? So here we want to say first n elements on the left side, minimize size, maybe add that later. I mean, I think for now it doesn't matter that much. But here we can keep track of sum left is equal to sum right is equal to 0. Just, you know, we have n is equal to length of nums, but we want to say, do I need this? I think we can, let's just remove this. Here, I just want to keep track of these two if I forget. But yeah, n3 is equal to n divided by 3, and we assert that n is divisible by 3, I think, or whatever. Yeah, 3 times n. Oh, well, yeah, you get the point. Yeah, and then now first n takes from the left side. Let's actually move this up, and then you can do. Well, n3 is actually my notation. Sum left at num sub I, right? And then also, oh yeah. Left is equal to sorted list, and then right is equal to sorted list, assuming that I spelled left correctly, right? Yeah, and then left dot add num sub I, and then same thing. First n elements on the right side for I in range of n3. Well, actually, I guess I deleted it, but you actually want all the numbers from n3 all the way to n on the right side, right? Yeah. Right, but then now we want to keep n elements on the left and right, and then on the right side, clearly, if this is n over 3, this is going to be 2n over 3, or 2/3 times n or whatever. I'm mixing n and n3, so it's my bad for the confusion, but you get the idea, right? It's just how we drew the sliding window, right? In the beginning. But then now you have to maximize it. So we maximize it by removing the smallest elements, right? N smallest element or n3 smallest elements, right? So here maybe we write something like 4, 2, and 3. We remove the smallest number, maybe this, something like that, or x is equal to this. Write that, remove x, and then some right subtract x, right? And then now, yeah. Now left has n. I mean, they both have n elements, but then you begin the sliding window, right? So maybe now begin the sliding window, and also now we can also say best is equal to sum left minus sum right, which is the function that we start off, but then now we slide. So then for I in range of n3 to 2 times n over 3, say, or no, just 2 times n. I mean, this is fine. N3 is already over 3. And then now sliding window means that we move num sub I from the right side to the left side, right? Okay, then first of all, we want to see if num sub I is in right, then it means that it is, what's it called, a largest number? It's maximized. That means that it is a large number. Maybe I'm doing this well, to be honest, because we remove a number, then now we have to keep track of this. Like, then now things get moved up, right? So maybe this part is wrong. I'm wrong here. Yeah, maybe I am wrong here, right? But what we can do is keep track of sum right. Yeah, okay. I'm trying to think whether there's a cleaner way of doing it, so give me a second. Give me a second. I mean, I think it's fine. I think maybe. So you could do it in two ways. You could keep track of everything on the right side, or you could keep track of or you could create a third sorted list. Is it a sorted list or just a set? Yeah, maybe I'll just keep a set of like floating, right? Yeah, let's do it that way. No, well, the thing is, okay, you remove something from the bigger half of the two-thirds, then now something from the floating would go to the right side, moving up, basically, right? Yeah, okay. This is kind of annoying, actually. I mean, but the idea is straightforward and easy to prove, I think, because you're just brute forcing everything. Not that brute, but yeah, I mean, I think this is fine. This is just the same, but more explicit, right? These are the numbers that did not make the list, but so then now we go, okay, well, yeah, if num sub I, so num sub I can be in two places, or one of two places, which is that it could be either being right or in floating, right? So that means that if nums, or if right that bisect left, okay, well, let's just say index is equal to this. It's a little bit awkward, but right, right. So if is there? I mean, do I have to bisect left? I think this is like an index. Let me Google sorted list syntax. I'm not gonna lie, I am like passing out, so that's why I'm like struggling a little bit. But I think there's an index though. That's why I'm like a little bit. Yeah, okay, there is. Well, but index may return an error. So let's see if there's a. I mean, maybe it is fine that it does, but contains. Okay, so there's a contain, which is actually what I need. Anyway, okay. So if, okay, so I don't have to do this way. So if num sub I is in the right side, APIs is always, because the thing is that I use so many languages that I forget which APIs in what languages sometimes, even though the idea is just the most important part, and it, but yeah. Then now we want to remove it from right. So then now we want to write that remove num sub I, right, and then some right subtract by x, or some num sub I x because I had it here, right. And then now if we removed it from the right, then now we have to add one from the floating to maintain the invariant that there are n elements, right. So then now we take the max element from the floating. So then yeah, we have f for floating, maybe, I don't know, floating of -1, which is the biggest element, and then that we remove it, f dot remove f of, oh no, floating dot remove f, okay, right. So then we remove it from the middle, if you will, or the ones that did not make the top n, and then we go right dot add f, some right add f, and then we maintain it, right. Okay, so that's the part about here, right. So if this is not the case, then f is equal, that means that it is in floating. So then we just do floating that remove num sub I, and that's it, right. There's nothing to follow up. It doesn't change num sum right, so no update there. And yeah, so we just remove it, and then part of that removal is that, well, now we're adding it to the left side, right. So then it doesn't really matter, but yeah, so then now we do left dot add num sub I, but then now num left has n plus 1 element, so we move the biggest, right? We want to remove the biggest because we want to keep track of the smallest. Yeah, we want to keep the smallest, right? So here we just go left dot remove the biggest number, maybe b for biggest number, and left dot remove b. Of course, you have to keep track of the sum left as a result of both. So let's do that. So you have sum left, num sub I, and then here sum left. We remove it, so we b, and then now we update best is equal to in this case a minimum of sum left minus sum right, and then now we're finally done. And I am passing out. I don't know if you could see it through the monitor, but my eyes are just like dripping out in a bad way. But yeah, unfortunately we're still not done yet. But yeah, well, let's put it out real quick. Maybe I'm off by 1. So we have left floating right, and if all goes well, then it should. Oh, I didn't add stuff to floating. I just kind of yeah, I just keep on removing the smallest number, but this should be put on floating. Floating.add x. I think I just forgot it. We typed a lot. Okay, so we don't need the print statement anymore. The print was because I got a thingy. But yeah. Looks okay for 1, 2, and 3. I didn't even know there was oh no, I put in the third case. But yeah, now we'll give a quick submit. Am I confident? I don't know. I'm just tired more than I'm not confident. But these 3 cases, especially this one, seems okay, so I'm happy about that. Apparently we are kind of on the slow side. I do wonder about that, but still gonna be fast enough. And what is the complexity here, right? It's gonna be n log n, right? Because here, you have n n log n, right? Even this is just n log n. It's n over 3 log n over 3, but still n log n. This is the same, right? This is also log n, right? Because the O loop, log n loop, and log n total, n of n loop, a couple of log n operations, maybe a lot of log n operations anyway, but still a constant amount, so it's gonna be n log n. Everything's n log n, and we're Gucci, we're happy, and Larry's gonna pass out. Even though maybe we could have optimized it a little bit more. Let's see what Larry did in the past. Because Larry in the past did mostly similar things. I think, like I said, I was gonna say you can actually use a heap, like I said, but and this code, maybe it's fine. I don't know. You could have to take a look at it. I don't know why it's so slow, but then maybe it's because we print. I do wonder. Or like it's so slow. Oh, well, it's also like 3 years ago now, so I don't know. More than 3 years ago. Is there a way I can just run this? That's what I was trying to find a button for. Why can't I run my own code? It is not clear unless I copy and paste this. Alright, I guess we are. Alright, let's remove the print statement. That probably didn't help. Looks okay. Let's go quick submit. See? And the reason why I wanted to do it, and you could probably watch my older video, the reason why I want to do it is because I wanted to show you the power of heaps. Yeah, we have a queue. Okay. I don't know. Yeah, I think this is roughly what I was doing, but using heap instead of sorted list. Heap is always going to be faster than sorted list because, well, that's just how it's operated. That's all I have for this one. Sorry, it's 40 minutes into this video, and today I just don't have the energy for it, the endurance for it, because I used up all my endurance running. But yeah, that's all I have for this one. Let me know what you think. Thanks for watching. Stay good, stay healthy, to good mental health. I'll see y'all later and take care. Bye bye.